morning, everyone. I'll be talking about static single assignment, aka SSA. This is an intermediate representation that is commonly used in production compilers like GCC and LLVM. This work proposes a new SSA form called as context-sensitive interprocedural SSA, and we'll talk more about this. So I'll begin with an introduction to what SSA is and what role does it play in program analysis. I'll take an example of program analysis to explain what do we mean by analyzing a program. And then I'll motivate the need for CoS-SSA. There's an introduction to something called as metamorphic assignment, which is customized to CoS-SSA, and then the future work. So SSA form is a property of an intermediate representation, which requires that every variable should be assigned only once. So what happens if you have multiple definitions? So this is achieved by renaming of variables. So let's say you have a variable x, and if it has multiple definitions, then you'll create different SSA versions for that variable x as x1, x2. And so by definition, then each SSA version is defined only once. And we want that exactly one SSA version should reach every use of that variable. So what happens if there are multiple, so if you have multiple control flow paths reaching a program point and you have a definition reaching along every path, then there's something called as phi function that is being introduced at the join point. So if you have, let's say, m predecessors to a particular node n, and every path has this definition coming from those paths, then you have this phi function introduced. Oh, sorry. Yeah, then you have this phi function basically, which takes all these definitions coming along different paths, and you introduce only a single definition. So after this, any use of u will be replaced by this definition un. And every definition of an SSA version dominates the use. That is also one property of SSA, and we'll take a look at it, why these properties are important for using SSA. So let's take a simple example. This is the original program where you can see that there are two definitions of x. So in SSA version, you will find two SSA versions, x_1 and x_2 over here. Now at this, just before this assignment, y is equal to x, you can see that there are two definitions of x reaching, this statement, which cannot be allowed in SSA. So what we do is we introduce a phi function over here. So we introduce x3, which is nothing but which could be one of the possibilities, x1 or x2. And now this x3 is used to define y1, which is nothing but an SSA version of y. Here, only one definition of x reaches this particular statement, which is x2. So this here we get z1 has been defined only by using x2. And here again, there are multiple definitions of x reaching this w is equal to x, and hence we introduce this phi function over here, and now x4 is used to define w1. All right, so as you can see, every definition, so what do we mean? So there was this last property which says that SSA version dominates the use. So from every path, from the start of the procedure to this particular use, you will have only one definition reaching along all the paths. So that's what we mean, and let's see what the repercussions of that particular property are. So let's take a look at why SSA is important for program analysis. So we take the same example, and we'll take a look at one of the optimization called as constant propagation. So for this optimization, you need to track what are the values for each variable is. And right now, I'll be throwing a lot of terms in terms of program analysis. I'll try to explain them with examples. Please do ask questions if something is not very clear. So there's something called as flow-sensitive analysis. So what flow-sensitive analysis means is that you compute program information, some information, so related to this constant propagation at every program point. And you follow the control flow of this particular procedure over here. So let's try to work out this example. So if I analyze this statement, x is equal to 10, I know that after the assignment, I know the value of x is going to be 10, which is a constant value in this case. If I analyze x is equal to 20, then that's the value that after the assignment, I know x is equal to 20 at this particular program point. So I'm computing information at every program point. Now let's try to compute the information for y. So in order to understand whether y will be constant or not, we need to know what x is, whether x is constant or not. So there are two paths reaching this particular assignment, along which one path, the value of x is 10, whereas the value of x is 20 along the other path. So we don't know statically which path will be taken, because for static analysis, we usually do not evaluate conditions. So at the join point, we assume that x would be non-constant. So this bottom over here means a non-constant value of x. And since y depends on x, Y also is considered as bottom. It is computed as bottom. It is non-constant for this particular example. Now, in this case, because only one value of x reaches, this particular value of x reaches this assignment, we can conclude that z is actually a constant whose value is 20. For w is equal to x, we have already concluded that after this assignment, x is a non-constant value, though we are getting a constant value along this path, but we conservatively assume that it's going to be a non-constant over here. And hence w becomes non-constant as well. So this is a flow-sensitive constant propagation. As you can see that you compute information at every program point, and it could be very expensive and also memory intensive. So there's another option for this where you do a flow-insensitive analysis. You ignore the control flow within the procedure, and you compute information, only one information at every program point. So let's start with, so since information is computed, one information computed at every program, we have a data flow information for the complete procedure. So we analyze x is equal to 10 first, and I don't know, somehow the highlighting is not happening. So for assignment x is equal to 10, we conclude that the value of x is a constant with the value 10. When we analyze x is equal to 20, we see that we've already computed the data flow information as x is 10 as constant, but now we've got another constant which is not the same value. So we conclude that x is non-constant anymore, is non-constant. Note that x is equal to 10 and x is equal to 20 are along different control flow paths. But this analysis is flow insensitive. We ignore the control flow, and that's the reason why after analyzing x is equal to 20, we infer that x is actually a non-constant value. But this is not true if you look at the program. Now, because x is non-constant, after analyzing y is equal to x, we come to the conclusion that y is non-constant. Similar, that goes for both z as well as w. Now, as you can see, that the z was actually a constant, is actually a constant whose value would be 20 in this particular program. But since we are ignoring the control flow and we assume that x would be non-constant, we get z as non-constant in this particular. The advantage of flow insensitive analysis is because you're maintaining only one information, it's more efficient, but the efficiency comes at the cost of precision, right? So now this will come into picture. So let's go back to the SSA version. Let's try to do flow insensitive analysis, which is an efficient analysis over the SSA. So because now we are not dealing with original source variables, we are dealing with SSA versions. So for x underscore 1, for the first assignment, we conclude that x underscore 1 is a constant with the value 10. X underscore 2 is also a constant with the value 20. Note that if we did the same analysis on the original program, we had concluded that x was a non-constant. But now because we have different SSA versions, we have different values for these variables. x3 becomes a bottom because it depends on x1 and x2 and both have different constant values. So this becomes a non-constant. And as a result, y1 continues to be a non-constant. But z1 gets value only from x2, which is a constant, and hence z1 remains a constant. x4 is a bottom and you have w1. So if you recall that we had the same analysis, so if you ignore the SSA, the underscore versions, this is the same result that you would get if you perform a flow-sensitive analysis on the original program, which is more expensive as compared to the flow-insensitive analysis. All right. So this is how you get efficiency as well as precision if you use SSA for program analysis. All right. So SSA plays a very important role, and this is what we want to exploit. However, so SSA gives you this benefit of referential transparency. So remember, there were three properties of SSA. One was there will be only a single definition for every variable, and every use will have a single definition reaching it, and that definition will dominate it. So because it dominates it, you can replace every occurrence of a variable x on the RHS of the assignment that defines x without worrying about where that definition comes from. We call that as a referential transparency. And this enables sparse analysis. So what do we mean by sparse analysis? You don't have to worry about the control flow completely. See, we did flow insensitive analysis on the original program. So we only look at the diffuse chains basically through the SSA versions. So that makes the analysis much more efficient, and also the optimizations. The limitations, however, are that most of the compilers that have this SSA as the immediate representation, they are restricted to local variables, which do not escape. And globals, address taken locals, and pointers are not handled by this SSA. And this is where we tried to mitigate this limitation, where we proposed something called as CoS-SSA, which extends it to the interprocedural level. I'll explain what do we mean by context sensitivity. And so basically, we are trying to use the benefits of SSA, but at the same time, try to reduce these limitations as well, using CoS-SSA. So before moving on to CoS-SSA, we'll introduce something called as metamorphic assignment. So we have seen 5 functions in SSA, right? So something similar to 5 functions, we have metamorphic assignments. So let's say you have an assignment x is equal to e. We represent that as a form of a metamorphic assignment, which is a collection of these assignments. And each of this assignment, it basically captures the behavior of an assignment executed along different interprocedural paths. So let's say you have this assignment in a procedure, and that procedure is called multiple times. So depending on what those definitions are reached along those interprocedural paths, we capture those behaviors in terms of these deforms. And each of these expressions is then identical to E, except that the variables in E are replaced by the SSA versions. So let's take an example in order to understand this. So let's say I have assignment A is equal to B plus C. I can very well replace this assignment as a metamorphic assignment where there are 2 definitions of A, depending on B1 and C1 and B2 and C2. So B1, C1 reach along one set of context, and B2 reach along the other set of context. And that's how we capture all the context that can be reached to this assignment. So the deforms in an MMA, they basically represent clones of the same statement, and they're distinguished by different sets of interprocedural paths. So that is what we mean by context sensitivity. So we analyze this particular statement depending on what the definitions are coming along different interprocedural paths. So let's take this example where there is a procedure P which has these 2 assignments T equal to input. So this input means read from input operations such as scanf. And there are use statements as well. This could be similar to your printf operations or your conditional statements. And so this procedure P has been called from 3 locations at call sites 3, 5, and 8. And you can see that there is an assignment on line number 13 which uses definitions of W and T. And you can see that there are different definitions of W reaching along different interprocedural paths. So let's take a look at what CoS-SSA would look for this. So this is an interprocedural SSA which performs naive cloning. So it clones every statement for every call reaching this. So there's a call through, so there are only one. Currently the nesting of call chain over here is only 1. So the call string is actually length 1. So for call along call site 3, we have T1 introduced. For 5, we have T2 and T3. And for calls along call site 3, we have definition W1 reaching. So we have W1 over here. Even along 5, we have W1 reaching. So this is W1. And for 8, there's actually W2 from node 7 that reaches existing. And hence we have X3 over here. All right, so obtain, this is statement cloning. It is unconditional cloning, and we do this for each context. So for every call string that reaches this particular statement, X is equal to W plus T, we create clones. And as you can see that there are actually multiple redundancies. So first thing is we capture only the dependencies. We don't capture what is the value of these variables. So we actually capture the dependency between T and X, W and X. So we are not concerned with what the values of T is. So in that case, the definition of T here is kind of independent. It doesn't depend on any internal source variables. So we can have only one. We could have only one definition for all of these contexts over here. In that case, if we stop making distinction between T1, T2, and T3, we realize that actually X1 and X2 are also equivalent. So these definitions of T1, T2, and T3, they are all redundant. Similarly, X1 and X2 is also redundant. So when we introduce CoS-SSA, what we do is we still do cloning of statements, but we do it on demand basis rather than unconditionally. So as I mentioned that we actually have only one definition of T1 in CoS-SSA, and because now there is no distinction between different values of T, There's no distinction between x1 and x2. We have only one clone for both the call sites 3 and 5. And this is what the CoS-SSA after minimization looks like. So it avoids redundant replications by combining multiple contexts. And this also helps because the previous method might not work for recursion, right? Because we could have multiple call strings reaching a particular statement. But with this, if we have a fixed, if a lattice is finite, we should be able to create this, these cloning practically. So this is another representation of CoS-SSA where we have, this is an original CFG. And what we did was we used the CoS-SSA and constructed these edges. So we had in the previous CoS-SSA, we had an edge from this W1 to this X1, right? And W2 to this X. But now we are not making, since this is the original source program, we don't have SSA versions over here. So we annotate these edges and we provide a routing table. And this routing table, so this routing table was not required for CoS-SSA because we had different versions, CoS-SSA versions. We are not making this distinction in the original source code. So we end up giving a routing table which helps you preserve context sensitivity by forbidding composition of some DU edges. So edge 1 will only be composed with 5, 6, and 7 according to the routing table. It will not be composed with 8 because that is a different context, which we got from the previous CoS-SSA version. So this is important because for now we haven't introduced CoS-SSA destruction. So we should be able to use this particular representation for performing optimizations. So if we go back to the, if we compare the classical SSA with CoS-SSA, you will realize that every SSA version is defined exactly once across all the procedures. And exactly one SSA version reaches every use, but here we have it along interprocedurally valid paths, because now we are doing it at an procedural level. And instead of just using 5 functions, we also introduce something called as metamorphic assignments. And the definition of an SSA version still dominates the use, but again, it is in the context of the interprocedurally valid path. So the characteristics of the original classical SSA still remain intact. They are now extended at the interprocedural level. We have implemented a reaching definitions analysis for constructing this SSA. And we've implemented that in LLVM. We also record context because we wanted to make context sensitive. The implementation currently works fine for non-recursive programs. However, we are facing some scalability issues for recursive procedures. We have some interesting ideas over here of incrementally doing reaching definitions analysis to scale this for recursive programs. The future work for this is basically we also want to handle pointers. So we have a good formalism where we do pointer analysis and reaching definitions analysis and try to context match between the two analyses and use this pointer information context sensitively. Then there's this notion of optimal placement of 5 functions, which will be addressed by the next talk by Supriya. And CoS-SSA destruction. So if you have the source program, you first construct a SSA over it, perform certain optimizations, which are machine-independent optimizations, and then the compiler destructs that SSA for machine code generation. So this that's there for SSA classical SSA in modern compilers, but we are yet to define CoS-SSA destruction for our SSA form, and maybe extend our current CoS-SSA to handle structures, heap, and arrays as well. With this, I stop. Yeah, thank you.
Many thanks to Pritam for this, introducing new paradigm on SSA. Yeah, any questions?
Good talk here, very good talk. You made 2 statements. One, you said if the lattice is finite, the constant propagation lattice itself is not finite.
Sorry?
You said this will work if the lattice is finite.
Okay, I should refine that statement saying that the height of the lattice has to be finite. Yes.
Second, you said it works fine for recursive, non-recursive functions. But can you tell a bit about the blow up that can happen in terms of the code, even if it is non-recursive function?
Sorry, could you please repeat?
See, you are adding additional assignment statements. Can you, and naturally the corresponding variables and all that.
Sure.
Can you give an estimate of the blow up? How much blow up can it happen?
So the blow up is actually linear. It's not exponential that way.
Are you sure?
Yes, at least through the experiments that we have seen practically, it is linear.
I mean,
So
to
we are
me,
doing,
I'll give a simple this thing, right? If I'm inlining every call site, if I inline, the blow up can be exponential.
yeah.
This is exactly that.
No,
F1 calls F2 twice. F2 calls F3 twice. F3 calls F4 twice. So inside F4, will you have exponential blow up or not?
yeah, so this is the one that will have the exponential blow up. When you do the cloning
No,
of
no,
the
here
statements
there are three
unconditional.
different call sites. I'm saying F1 calls F2 only twice. F2 calls, inside the body of F2, there are two calls to F3. Inside the call to F3, there are two calls to F4. Now, inside F4, corresponding to each effect, you will have a tip. Kind of inlining funda says it should be, you may have an exponential blow up unless you do something smarter.
Yeah, so when you're doing inlining, you're actually considering all the control flow paths. So there'll be multiple interprocedural paths that you'll have to consider, and you'll do the inlining based on that, right? But what we are trying to do is we are trying to identify, are there any, so if we can distinguish those interprocedural paths based on the definitions.
You're doing something smarter.
Yeah, so that's where, so this is unconditional cloning happening over here. There are three calls, direct calls, the ones that you're saying would cause but this one over here, where we actually do replication based on that.
So the answer to that question is we use value context.
Yeah.
And so our experiment actually showed sublinear this thing. 95% is what we got, 0.95. So less than double the number of this thing.
Size. Again, the routing table will also be considered based on the value context and not on the interprocedural paths. So if you look at the routing table, it's not the control flow paths, it's the dependence edges. It's the dependence edges between the definitions and the users. These we don't expect it to be exponential. Again, if there are nested calls, if the definitions reaching along them are identical, then you would have only one diffuse edge between, even if they are nested calls.
A quick question, Pritam. Nice talk.
Thank you.
I didn't see any performance numbers on downstream tasks, because if you are taking so much hit in terms of doing extra analysis, what kind of additional performance are you seeing on downstream tasks?
All right, so this is work in progress right now. We are working on the prototype implementation. It's not complete yet. So we don't have the numbers. We have some preliminary results which show us the benefits of better. So we were able to identify more constants as compared to the ones that we were able to without CoS-SSA, without the interprocedural CoS-SSA. But we don't have the exact numbers right away.
So maybe next IICT, next year. Just one remark about Krishna's question about the height of the lattice being finite. Here, the lattice that we want is lattice of the definitions. So it's a lattice of reaching definitions, which is finite. So it's not that's why it works for recursion. The number of definitions, static definitions in the program is bounded. Even if you have recursion, the number of definitions it still remains fixed. So you just have a lattice of that. So it works well.
Okay, so let's speaker once again. Now,